we need kind of a higher voltage than the cathode ray situation. Why we need some pressure which is actually greater than the observation of the cathode rays. Why these scientists are saying that positive rays are actually originated near to the anode, not near to the cathode but near to the anode. So you won't observe any kind of rays appearing here if they are to drag back to the negatively charged plate. That will happen if the rays are originated from here. Why is that? Even without the closed circuit situation, right? When you are with a very low amount of gas particles inside a tube, inside a container, what happens is those get ionized. Those get ionized with normal temperatures. When the mass drops, EOM ratio increases, no? Right now, when the mass drops, EOM ratio increases because you are carrying the same charge. When the mass drop, the ratio increases. So EOM ratio of H plus is a greater value than the O plus. Good evening, Lamai. Let's start the class for today's lesson. Right, last day actually we had discussed about the cathode rays, right? So the origin of cathode rays, the Crookes tubes, right? Then how they were produced and the properties, and finally we had discussed about the finding of the electron as well, right? And it's some of its properties. I mean the electron's properties, the mass and the EOM ratio, right, and the charge as well, right? So that was the discussion last day. Today we'll start from we'll continue from the cathode rays, right? Okay, so today we are going to discuss about the positive rays, the canal rays. Okay, right. Let's think of this, right? When they have found the negative particles, the fundamental negative particle, the electron, right? The scientists thought of there should be a oppositely charged particle in atoms, because we know, all of us know, that atoms are neutral. So as atoms are neutral, there should be kind of oppositely charged particles for the electrons, right? There should be kind of oppositely charged particles to neutralize the charge of electrons, right? So they are searching for that oppositely charged fundamental particle, right? So the first evidence of these positive particles is actually came through a practical of Eugen Goldstein, right? Eugen Goldstein was the scientist who came up with a successive setup, experimental setup for finding out the positive rays, right? Let's discuss about the setup created by the Eugen Goldstein, right? It is known as the canal ray tube. Let's discuss about that thing today, right? Okay, the Eugen Goldstein, right, came up with this kind of a setup, right? It is also actually a cathode ray tube, right? But with a little difference, right? What was the difference? Instead of the normal cathode, he had used some cathode with some holes in it, right? Some holes in some canals were there in the cathode of the Goldstein's tube, right? This was the idea, right? So he had came up with a tube like this, right? So basically it is with some holes in it, right? This is the cathode ray tube constructed by the Eugen Goldstein, right? So this was his cathode, right? And there was anode too, right? And he connected these two terminals to a high voltage, like 10,000 volts, let's say, right? This was the experimental setup which the Goldstein made, right? So this is so let's label the stuff, Lama, before discussing, right? Let's label this stuff, right? This is the anode, which is connected to the positive terminal, and here you have the cathode, and this is a special kind of cathode, right? Which is known as a cathode with some holes, some canals in it, right? So it is actually a perforated cathode. Some holes or canals were there in your cathode, right? So it is referred as perforated cathode. Right, and there was a vacuum. There was a kind of situation, some pump to release some gases in it, right? So this was a setup, right, done by the Eugen Goldstein to observe the positive rays, right? Let's see what was his observation. Actually, when he came up with this setup and connected the two terminals to this kind of a high voltage, he had seen some rays are actually coming from these holes, through these holes of the perforated cathode. He had seen some rays are coming through the holes of the perforated cathode, right? That was the first observation of positive rays, right? So such kind of rays are coming through the perforated cathode, right? That was the first observation of positive rays, right? Then we'll discuss how these rays came like this, right? What is how these rays produced, what is the origin of these rays. We'll discuss about that, and let's discuss and then we'll discuss about the voltage they have used and the mechanism of producing the anode or the canal rays, right? Okay, this was a setup, right? Okay, so few important points are there to discuss here, right? In this case, to observe these canal rays, right? They have used kind of a high voltage. Actually, that voltage is a bit more than the voltage used in the cathode ray tube, right? Here for the to observe the positive rays, right? They have used some greater voltage than the observation of the cathode rays. Let's discuss why they wanted such a high voltage to observe the canal rays, right? That is first thing we need to discuss here. And the second thing, right, when it comes to the pressure, inside the tube, right, it was a bit higher value than the cathode ray situation. The pressure inside the tube was a bit higher than the observation of the cathode rays, right? There is a reason for that. We have to discuss about that thing as well, right? And then they have ultimately concluded, even though they see these rays are coming from the canals, right, of the cathode, with some experimental evidences, they have concluded that these rays are actually originated from the gas inside the tube, right? They are ultimately confirmed that these rays are coming from the gas inside the tube, right? And basically from the gas inside the tube, which is near to the anode but away from the cathode. That was the idea, right? So these rays originate from the gas inside the tube and actually bit closer to the anode but away from the cathode, right? We have to discuss about the reasons for that conclusion as well, right? Those are three things now we are going to discuss about this experiment, right? Why we need a greater voltage than the cathode ray situation, right? And then why we need a bit higher pressure than the observation of cathode rays, right? And then we need to discuss about why they have concluded that the cathode rays are originated from the gas inside tube, and those originated from gas inside tube bit near to the anode but away from the cathode, right? Let's discuss about the reasonings for those observations, right? Okay, first thing, basically, right, we need kind of a higher voltage than the cathode ray situation. Let's see why. The reason is this: the voltage needed here, the point is voltage needed to observe anode rays or the positive rays is actually higher than the observation of cathode rays. Let's discuss about this idea. Why we need such kind of a greater voltage than the observation of cathode rays. Right? What is the idea, Lama? Any idea? Can anyone guess why we need kind of a higher voltage here than the cathode ray situation? Any idea? No. Okay, I'll tell you. Right? The reason is this. Right? So, actually, the anode rays or the positive rays are actually originate from the gas inside tube. Those are not the electrons. Actually, those are kind of gas particles, right? Those are originated from the gas inside tube. It is not originated from the anode or the cathode, but originated from the gas inside tube, right? So these are actually positively charged gas particles, so positively charged ions, right? As those are positively charged ions, those are with some greater mass than the electrons. Ions, right? Positive charged ions means those are with protons as well, protons and neutrons as well. So that their masses are greater than the masses of electrons, right? So when it comes to the kinetic energy, so we see the movement of these particles, right? When it comes to kinetic energy of these positive rays, right? When it comes to kinetic energy of the positive rays, right? It should be a greater value as you are dealing with kind of a higher mass than the electrons. In the case of electrons, right? In the case of cathode rays, you came up with a lower mass, but here you are dealing with a higher mass, the positive ions, right? Mass is high, so you need kind of a higher kinetic energy to move these particles towards the cathode, right? So to provide the higher kinetic energy, basically you need a high voltage, high electrical energy. The high electrical energy is the one we use to provide this high kinetic energy which is needed for positive rays to move, right? So that is why we need kind of a greater voltage than the situation with the cathode rays, right? See, that is idea is clear now, right? As those positive rays originate from the gas inside tube, right? So their masses are high because protons are also there here, right? Protons, neutrons are there inside the ions, right? So their masses are higher than the electrons. So mass is high means they need some greater kinetic energy to move them, right? So that greater kinetic energy should be supplied by the voltage, the electrical energy. So that you need to supply some higher electrical energy by a higher voltage, right? That is the idea, right? That is why we say we need some greater voltage than the situation to observe the cathode rays, right? Okay, so to observe the anode rays, we need some greater voltage than the situation of the cathode rays, right? Okay, that is one specific thing you need to know, right? Second one, why we need some pressure? Why we need some pressure? Which is actually greater than the observation of the cathode rays, right? So the second point is actually, right, the pressure inside the tube. Pressure inside the tube when observing canal rays is actually greater than the situation with the cathode rays, greater than the observation of cathode rays. let's discuss about that thing, right? The idea is this, Lamai. So actually, to observe positive rays, right, we need some gases, some gas particles inside the tube. The canal rays are the gas particles. Canal rays are originated from the gas particles, gases inside the tube, gas molecules, from the gas molecules inside the tube, not from the electrons or anything. So you should have some sufficient amount of gas molecules inside the tube. Without some sufficient amount of gas molecules inside the tube, you won't observe the anode rays. You won't observe the anode or the positive rays. Positive rays are actually originated from the gas inside the tube. So some gas particles should be there, some sufficient amount of gas particles should be there to observe the positive rays, right? So that more gas particles in the tube, inside the tube, means more pressure. So last day we had discussed about that pressure is originated by the gas molecules, right? When more gas molecules are there, right? When they hit the walls of the container, there you will feel some greater pressure inserting on walls, right? So more the gas molecules, more the pressure is. So we need some more gas molecules into the tube to observe the positive rays, because positive rays are actually originated from the gas molecules. So need some sufficient amount of gas molecules so that some pressure will be there, which is actually greater than the cathode ray situation, right? So to observe the cathode rays, we don't need gas molecules, right? So if the gas molecules were there, it is hard to cathode rays to go through the gas molecules, right? That is a problem at the cathode ray situation. But that is not the case with the positive rays, right? As the positive rays are the gas molecules, the gas positively charged ions, right? So you need some sufficient amount of gas molecules to observe the positive rays. So the pressure should be a bit higher than the cathode ray situation, right? That is the idea there, right? Okay, next one. Why they are saying, why these scientists are saying that positive rays are actually originated near to the anode, not near to the cathode, but near to the anode, right? Away from the cathode, but near to the anode, basically away from the cathode, right? The positive rays are originated away from the cathode. That is very important observation, right? So we'll write that thing as well. Actually, the positive rays, right? So we'll copy another color. So actually, you can see the positive rays are originated right from the gas inside the tube, but actually it is closer to the anode, away from we'll write here, close to the anode, away from cathode. Positive rays are originated from the gas inside the tube, closer to the anode, but away from the cathode, right? This statement is there in your research book, right? So we need to know why is that, right? The thing is this, Lamai. So if some positive rays are to originate from here, suppose rays are to originate from here, right? What will happen? Can anyone guess what will happen if the positive rays are to be originated from the cathode, near to the cathode? What will happen? So the point is, Lamai, these are positive rays now. Your cathode is negatively charged. Right? As these are positive rays now. So what will happen? Right? Basically, when the positive rays are coming out from the canals there of the negative terminal, right? What will happen? As those are positively charged, those will drag back to the cathode now. When they are coming out from the cathode, as those are positively charged, those will drag back to the negatively charged plate. So you won't observe any kind of rays appearing here if they are to drag back to the negatively charged plate. That will happen if the rays are originated from here. Why is that? If the rays are originated from here, right, so their acceleration toward the cathode is not that much enough to overcome the drag by the cathode. So if the positive rays are originated from here onwards, they are accelerating towards the cathode. So at this stage, they are with a great acceleration, which can be used to overcome the drag by the cathode again, right? But if they are accelerating only from here, if you are accelerating only from here, from the cathode, that acceleration power won't be enough to overcome the drag back from the cathode. That was the idea. So that to observe the positive rays coming from the holes of the cathode, surely they should originate from far away from the cathode. Then only high acceleration ultimately leads you to, right, overcome the drag of the cathode and come out from the holes of the cathode, right? So that is the idea. So that is why they are saying the positive rays are originated from the gas inside it, but far away from the cathode but near to the anode. That is the idea, right? So those are some clear ideas, right? You should know, right? Those will be asked in your papers, in MCQs as statement questions. Those will be there, right? Okay. So this is all about the situation, right? The positive ray tube constructed by the Goldstein, and some specific ideas, right? Special ideas were discussed here. Okay. So Lama, you can draw this stuff, right? You can draw this stuff, right? Just draw this one. Okay. Just draw this setup, right? Some perforated cathode is there. Means some cathodic metal with some holes in it, right? So they have seen some rays coming out from the perforated cathode, right? That was the observation, right? Okay. So these are canal rays, right? These are canal rays. Even these. Remember that those are originated from away from the cathode but near to the anode, right? Let's write this stuff. Right, okay. Let's write. After drawing this thing, just drawing this thing is enough, right? Just write the stuff, right? Okay, let's write. At the given space, just write this, right? When a high voltage of about 10,000 volts, in a high voltage of about 10,000 volts was applied across the electrodes, a faint real glow was observed. Behind the perforated cathode. They have seen some glowing behind the perforated cathode, right? Behind the perforated cathode. Next line, at the next line, just write. These rays are called. Come to the red color and write. Canal rays. Come Come to the normal color again. Come to the normal color. Because they were produced by the holes, because they were produced by the holes, because they were produced by the holes or canals in the cathode, or canals in the cathode, because they were produced by the holes or canals in the cathode. Right? Okay. At the next line, come to the next line and write. Although the rays are, although the rays are, although the rays are, although the rays are, come to the red color pen and write, come to the red color and write, not exactly formed at the positive electrode, not exactly formed at the positive electrode, although the rays are not exactly formed at the positive electrode, comma, or the anode, not exactly formed at the positive electrode or the anode. So remember that, right? Cathode rays and the positive rays are not generating from the anode, right? It is not generating from the anode like in the cathode ray situation. In cathode ray situation, the cathode rays were produced from the cathode, right? But when it comes to the anode rays or the canal rays, those are not producing from the anode, right? Those are producing from the gas in the tube, right? Let's write that stuff right? Come to the normal color and write. Come to normal color and write. Since they are formed away from the cathode, 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 closer to the anode, closer to the anode, since they are formed away from the cathode, closer to the anode, they were also known as, 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 come to the red color and write, anode rays, anode rays, they were also known as anode rays. Come to the normal color, O, again in red color, positive rays, O, positive rays, right now? That is the whole idea about that experiment done by the Goldstein, right? This was the first observation of positive rays, right? Using his perforated cathode, that tube including the perforated cathode, right now? Right, okay. Now let's discuss about the mechanism of producing these rays. How these were produced here, how these canal rays were produced. Let's discuss about that thing now. So in your note, there's a space for the mechanism, to write the mechanism of producing positive rays, right? Okay, let's discuss about that thing as well, right? Okay, how these rays were produced, that is the next discussion, right? Let's discuss about that, how these rays are to be produced in this special tube, the canal ray tube, right? Okay, the idea is this, right? The idea is this. Let's see how these are to be originated from the gas inside. Okay, let's see. Now we are discussing how these positive rays were produced, right? From the gas inside, right? Okay. The point is this. Lamai, right? When we are thinking of a situation with some low pressure, right? When we are thinking of a situation with some low pressure, remember that here also we are carrying out some low pressure situation, right? But that low pressure is smaller than the sorry, that low pressure is greater than the pressure of the cathode ray situation. It is like this lemma. So let's say, so this is 1 atm, this is 1 atm, that is 1 atm. Let's say this is the pressure, normal atmospheric pressure. So if this is 0, let's say 0 pressure, 0 atm. If the pressure used in the cathode ray tube is like this, if the pressure used in the cathode ray tube is like this, right, for the cathode ray situation, the pressure we are using for the anode rays is like this, anode or the positive rays. Still keep it in mind, right? Still keep it in mind. It is also still, it is a low pressure. Still it is a low pressure, which is near to the 0. It is still a low pressure. That is this 1 atm is here, right? It is still a low pressure compared to the atmospheric pressure, but that pressure is bit greater than the cathode ray situation. We have discussed why we need such a bit greater pressure, right? Anyway, it is kind of a low pressure, right? Still maintaining to observe the cathode anode rays, right? Okay, let's discuss how the what is the mechanism here. Now, when we are dealing with low pressures, right, that means we are with very few gas particles. When we are dealing with low pressures, right, we are with very few gas particles. Very few. Low pressures means amount of gas particles are less, right? We had discussed that thing at the last lesson, right? Okay, let's go to the last lesson and see what happens there, right? Why the pressure is low when the amount of gas particles are lower. Anyway, right? So we are with less number of gas particles here, so that right, so that the energy, let's say, even without this, without the closed circuit situation, right, when you are with a very low amount of gas particles inside a tube, inside a container, what happens is those get ionized with normal temperatures. Even at 25 Celsius, normal room temperature, we would see some gas molecules which are ionized by releasing electrons. We would see some gas particles actually which are ionized in this kind of low pressure, right? We won't see this kind of ionized gas particles in normal pressures, right? In normal 1 atm pressures we won't see this, but in very low pressures this will happen. In very low pressures, even at 25 Celsius, right, some of the gas particles will get ionized. Why is that? Anyone have any idea why we are able to see some ionized gas particles with low pressures? Why we are able to see those? Not with high pressures, but with low pressures we are able to see some ionized gas particles. Why is that? The gas particles here are not ionized, no? Gas particles here close ourselves are not ionized, no? That is what with 1 atm, no? But when it comes to very low pressures, actually we have few gas particles, and those most probably those few gas particles are ionized, right? Few gas particles and some of those are ionized. The reason is this, Lama. The idea is this. See, let's get the clear idea there, right? The idea is this, right? It is like this. So let's discuss about two systems. Right? This is a system with more number of gas particles. High pressure. Maybe like a 1 atm or something, right? So this is another system with low number of gas particles. That means low pressure. right? Lithium amount of pressure, right? So let's say 10 to the power minus 3 or minus 5 ATM, very low pressure, right? At that situation, what will happen? At that situation, what will happen? Right? It is like this. Let's say both of the systems are with 25 Celsius temperature. So 25 Celsius temperature means in that system there is kind of thermal energy. With 25 Celsius, associated with the 25 Celsius, we have some thermal energy inside the system. Temperature is there means some thermal energy is there. Let's say that I'm just taking some numbers, right? Just some number, right? Let's say with 25 Celsius, we can count that number, but just to imagine, right? Let's say you have just 100 joules there, 100 joules of energy with the 25 Celsius situation. 25 Celsius carries some 100 joules there. For this 25 Celsius also carrying some 100 joules. The thermal energy with the temperature, right? But in this case, some special thing happens. This 100 energy will be absorbed by only 5 particles. This 100 joules of energy will be absorbed by only 5 particles. Let's say only 5 molecules are there. 5 molecules are there. So 100 joules of energy will be absorbed by 5 gas molecules. Let's say you have 100 molecules here. That means 100 joules will be absorbed by 100 molecules. That means one molecule absorbs only 1 joule of energy. 1 joule per molecule. Here it is 100 over 5, 20 joules per molecule. So what will happen here? If the 20 joules are sufficient to supply the ionization energy of these stuff, those will eject electrons and get ionized. Right? Let's say the ionization energy of these kind of gas molecules are equal to 15 joules. That means here these gas molecules won't get ionized, but here those get ionized because you are providing more energy than the ionization energy. This is the minimum energy you need to ionize a gas particle. So now the gas particles feels more energy. So the gas particles will eject those electrons by absorbing that energy, 20 joules of energy, and eject those electrons. That means we are with now some positively charged gas particles in this kind of system with low pressures. But that thing won't happen with systems with high pressures. Got the idea, right? So when we are referring to systems with low pressures, we are able to see kind of ionized gas particles, not with these systems, but with here you see kind of ionized gas particles even without applying the voltage. So remember that, right? Even without applying the voltage, you will observe very few amount of ionized gas particles in an anode ray tube. In an anode ray tube, even without the voltage applied, right? You will see little amount of gas particles, right? Ionized gas particles, as you are dealing with kind of a low pressure, very low pressure, right? Okay, no? Right, that is the idea. So you have some positive particles, right? You have some ionized positive particles like this. Few positive particles are there, right? Few positive particles are there, ionized positive particles are there in the tube, right? Few ionized positive particles are there, and unionized particles are also there. Right? Okay. So if you are before the application of the voltage, you have ionized as well as unionized particles, gas particles. So when the switch is on, when you on the switch here, what will happen? This becomes negatively charged terminal, so that these ionized particles start to travel towards that negative terminal. These positively charged particles starts to travel towards the negatively charged terminal. Right? Start to travel towards the negatively charged terminal. These few of the positively charged particles. So what will happen then? When these guys hit the unionized particles, they will transfer their kinetic energies to the electrons of the unionized particles, and those electrons will be removed as well. Making some more positively charged particles. Removing electrons, you will come up with some more positively charged particles. Right now? That is how the positive particles are generated. Inside the canal ray tube. That is how the positively charged particles, more of positively charged particles are generated. Right? Then what will happen? If the particles are generated from here, the particles generated from here are actually, when they are accelerating towards the cathode, right? Those are able to overcome the drag, right, done by the cathodes, done by the perforated cathode, right, when they are going through the holes, right? That is why we say only the ones generated near to the anode, away from the cathode, coming out from the holes of the perforated cathode. Not these ones. These ones won't have such amount of acceleration power or force to overcome the drag again, right, done towards the cathode, right? That is why we say those are not able to come through the holes of the perforated cathode, right? So only the positive rays coming from here, positive particles coming from here, are able to go through the holes of the cathode and come out, right? So that is the idea. So that is how you generate the positive rays from this tube, right? Okay, got the idea, no? Right, let's write this stuff. Right, right? This is about the mechanism of producing positive rays. This is the mechanism of producing positive rays. Let's go through this stuff, right, one by one. First point number 1, right, like this. When a high voltage is applied, you don't need to draw this stuff, right? Let's write this thing. When a high voltage is applied, its electric field accelerates the small number of ions present in the gas. When a high voltage is applied, its electric field accelerates the small number of ions present in the gas. Right now, small number of ions present in the gas. Second point number 2, second point, right? These ions collide with atoms of the gas. These ions collide with atoms of the gas, knocking electrons off of them, and create more positive ions. more positive ions. Right now, and create more positive ions. Right. Next one, third point. These ions and electrons in turn, these ions and electrons in turn, these ions and electrons in turn strike more atoms, these ions and electrons in turn strike more atoms, and create more ions and create more and more positive ions. Create more and more positive ions. These ions and electrons in turn strike more atoms and create more and more positive ions. Create more and more positive ions. Right now. Next point. Copy the next point. The positive ions are attracted to the cathode. The positive ions are attracted to the cathode. The positive ions are attracted to the cathode, and some passes through the holes in the cathode. Some passes through the holes in the cathode. Got the idea, Lama? If a positive ray is coming directly towards the cathode, they will stop at the cathode, right? But if some positive ray is coming directly towards the holes, towards the hole of your perforated cathode, then they are able to go through the holes if their acceleration power is greater, if they have sufficient energy to overcome the drag done by the cathode, right? So that is the idea there. Not all the positive rays are able to go through the holes of the cathode and comes out at the cathodic side, right? But some are able to do so. Basically, the ones which are directly coming towards the holes of the cathode, only if they are with sufficient energy to overcome the drag done by the cathode, right? They are able to come out as canal rays, right? That is the idea, right? Okay, right. That is actually how the canal rays are produced, right? Parallel. Okay. Do you have any questions, Lama? Do you have any questions about the discussion here? Questions? Any questions about the discussion here? Up to you, no? No. This time, no? Right. Clear. Right. Okay. So let's discuss about the properties of positive rays. Let's discuss about the properties of positive rays. Right. Properties of positive rays. So when we are discussing about the properties, right, you will see some properties same as the cathode ray situation, right? When it comes to positive rays, you will see some properties are same as the cathode ray situation, but sometimes the opposite things are there, right? Let's see what are the properties of canal rays. Properties of canal rays. First thing, actual lamai, positive rays also travel through straight lines, right? Traveling straight lines, right? You can come up with the experimental setup, right, for the positive rays as well, and you will see the shadow. There, like in the cathode ray situation, right? You can do the same setup, right? You can copy the same setup, right? With the use of positive rays as well, right? So positive rays are traveling in straight line. Just write that there, right? Number one, they travel in straight lines. as the same experiments are carried out, right? I'm not going to explain that much, right? Just write this stuff, right? The first one, they travel in straight lines. This is the page number 9, right? The properties of the positive rays, right? They travel in straight lines. They travel in straight lines. At the next line, put a dash and write. Put the dash and write about the experiment we can do to prove that, right? Put a dash and write. Cast a shadow. Cast a shadow. Cast a shadow of the objects. Cast a shadow. Cast a shadow of the objects placed in their way. Placed in their way. Cast a shadow of the objects placed in their way. Right? Cast a shadow of the objects placed in their way. Right. Number 2. Number 2. The second property. Right? Actually, the positive rays are also with some momentum. Like in cathode ray situation, the positive rays are also with a momentum. I mean, it is with a kinetic energy. We had seen that with a kinetic energy means it is with a mass and a velocity. The kinetic energy is half mv squared now. Positive rays moves now. So kinetic energy is there. That means half mv squared is there. That means m and v is there. That means positive rays are with kind of momentum, right? Just write the stuff, right? They have a momentum. Number 2, they have a momentum. These are properties, right? Number 2, they have a momentum. They have a momentum. Within brackets you can write. Within brackets you can write mass and kinetic energy. Mass and kinetic energy. They have momentum within brackets mass and kinetic energy. Mass and kinetic energy. They have momentum within brackets mass and kinetic energy. Right? Put a dash and write. Put a dash and write. What kind of experimental setup we can come up with? Yes, the setup is actually we can again come up with a parallel veil, right? In the path of the positive rays, right? You will see that parallel veil moves, right? So that is the same experiment you have done to prove that the electrons are with some momentum, right? The cathode rays are with some momentum, right? The same experimental thing can be done here as well, right? So put a dash and write. They can move a parallel veil. They can move a parallel veil. They can move a parallel veil placed in their path. They can move a parallel veil placed in their path. Right? They can move a parallel veil placed in their path. They can move a parallel veil placed in their path. Right, no? Okay. That was the second property. That was the second property. Right. The third property. The third property of positive rays. Just write this thing. Then I'll explain. First write the one, right? Third property. These rays are positively charged. These rays are positively charged. These rays are positively charged. Right? These rays are positively charged. Right? So you can prove that as well using external electric fields and external magnetic fields, right? So the point is this now, right? You can think of some canal ray tube like this. You can think of a canal ray tube like this with some hole here. This is your positive terminal, right? This is your negative terminal, right? Negative terminal, right? Means this is your anode. This is your cathode. So the positive rays right? The positive rays which travels through the hole will come out like this, right? The rays which travel through the hole will come out like this. So you can place kind of a external electric field here. You can place kind of a external electric field here. External electric field here. What will happen? External electric field, right? External field. Right? Let's say this is the negative terminal and this is the positive terminal of the external field. What will happen? These positive rays, right? These positive rays will deviate towards the negative plate of the external field, right? The positive rays or the Cannon rays will deviate towards the negative plate, the opposite charge plate, right? So that we can prove these positive rays are, or the Cannon rays are positively charged. So these are the Cannon rays, right? These are the Cannon rays. So Cannon rays move towards the negative charge plate of the external field, right? So we can say, as Cannon rays are moving towards the negative plate, the Cannon rays should be with the opposite charge, the positive charge. So the Cannon rays are positively charged, right? That is the idea, right? So we can come up with a external magnetic field as well. To prove this idea, you can come up with the external magnetic field as well. Let's prove this stuff as well. Okay. So you can think of a external magnetic field as well. Now we are just trying to prove the charge of the Cannon rays, right? So you can build up this kind of setup as well, right? This is your anode, this is your cathode with some hole, right? So the anode rays originate from the gas inside tube will travel like this, right? Then you can place some external magnetic field here. You can place some external magnetic field here. External magnetic field here. Right? Let's say this is south, this is north. Right? So these rays will deviate. Right? And those will come here. When they feel the presence of the magnetic field, when they feel the presence of external magnetic field, right? What will happen? This is how the magnetic field operates, right? What will happen? Those will get deviated. But remember, like in cathode ray situation, right? These guys will get deviated not towards any of the poles. Remember this. Not towards any of the poles. Basically, the deviation is kind of, perpendicular. It's kind of perpendicular to the magnetic field. See, it is perpendicular to the field. Not towards any of the poles. Yes, it will come towards ourselves. Some deviation is there, but it is perpendicular to the magnetic field. So, so that with this thing also we can say that the positive rays are actually charged particles, and this deviation direction is actually similar to the deviation direction of the all the other positively charged particles, so that we can say these are positively charged. So you can apply this Leibniz left hand rule as well. Leibniz left hand rule could be applied here as well, right? So then also you will see the deviation direction, right? And you can think of the situation here, right now. So that is how we prove that positive means the Cannon rays are positively charged particles, right? Okay, with the use of external electric field and an external magnetic field. Let's write the two stuff there, right? Number 3, right? Number 3. Let's continue the properties, right, of positive rays, right? Number 3. These rays are positively charged. These rays are positively charged. These rays are positively charged. These rays are positively charged, right? Okay. So write like this. Put a dash and write. Put a dash and write. When an electric field is applied, 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 in the path of the rays, in the path of the rays, in the path of the rays, when an electric field is applied in the path of the rays, put a comma, and write. They are, write it in red color, deflected towards the negative plate, deflected towards the negative plate. They are deflected towards the negative plate. You see the deviation angle, right? They are deflected towards the negative plate, the opposite charge plate. The Cannon rays are deflected towards the negative plate, right? Of the, come to the normal color, right? Of the electric field, of the electric field, of the external electric field, the Cannon rays are deviating towards the positive terminal. So if some particle is deviating towards the positive terminal, coming towards the positive terminal, that means that particle should be with the opposite charge. They are deviating towards the negative terminal, so that those should be positively charged. Cannon rays are deviating towards the negative terminal, so that the Cannon rays should be positively charged. Right now. Okay. Next point. It is about this one, right? Next point. Next one. When a magnetic field is applied, when a magnetic field is applied, when a magnetic field is applied, when a magnetic field is applied in the path of the rays, in the path of the rays, in the path of the rays, when a magnetic field is applied in the path of the rays, they are, write it in red color, write it in red color, deflected, see, they are deflected, they are changing their path here, they are deflected, come to the normal color, and the direction of deflection is, and the direction of deflection is, and the direction of deflection is, direction of deflection is opposite to that of cathode rays, opposite to that of cathode rays, opposite to that of cathode rays. Direction of reflection is opposite to that of cathode rays. That is the idea, right? So actually you can come up with the direction here by applying the Fleming's left hand rule, right? Let's apply this stuff, right? Fleming's left hand rule. FBI, no? F means the force, that is the direction of particle movement. When you are applying force towards that direction, the particles will move, right? If B means the magnetic field, I means the current flow, right? Let's apply this stuff. These are positive particles, so we can apply the current flow like this. Current flow. B, this is B. This is B. B means the magnetic field from north to south. Magnetic field from north to south. Right? And this is the I. This is the I. I towards us. I towards us. This one. Here. Towards us. Right now? Force towards us. B, the magnetic field from north to south. I, the current flow, the positive charge flow, that is here. So you clearly see the deviation is towards us, right? Okay, that is the idea, right? Okay, so these are deviating, right? The deviation deviating to not towards any of the poles, but perpendicular to the magnetic field, right? That is the idea. And the direction of deflection is actually similar to the all the other positive charge particles, right? And opposite to the cathode ray situation, right? No, okay. So that we can confirm these positive rays are positively charged. That is clear, right? The positive rays are positively charged, right? Next one, right? Next point, right? Then let's come with the fourth point. This is the most important point, Laman. Right? This is the most important point. This is the most important property when it comes to positive rays, right? Okay. The idea is this, right? This is all about the deflection angle. This is all about the deflection angle, right? Deflection angle. See. So earlier we had discussed this deflection angle, theta, is the deflection angle, right? Deflection angle. If you think of the deflection angle, that theta is actually proportional to EOM ratio, Lama. Earlier we had discussed deflection angle is proportional to charge over mass ratio, right? Greater the charge, the angle will be greater, and greater the mass, the angle will be lower, right? So we had discussed about that in last day, right? So let's discuss about the same thing for the positive rays as well. Last day we had discussed about this thing for the cathode rays, and we have seen even though you have used the same kind of gas inside the tube, even though you have used the same, even though you have used different kind of gas inside the tube, even though you have used different kind of metals as the cathode, still you got the same deflection angle when it comes to cathode rays. That was the observation in the cathode rays. Deflection angle was same with different gases, with different metals as cathode, right? You got the same deflection angle, right, with the cathode ray situation, right? So that is why we confirm that from each and every matter, from all the stuff, you get the same particle, right? Same negative particle, because EOM, the charge or mass, is the same. The same particle is producing from all the kind of matter, right? That's how we confirm, right? How the Thomson confirmed that thing, right? So now today we are going to discuss about the positive rays, not the cathode rays, positive rays, and let's see what happens with the positive rays with these deflection angles and the EOM ratios, right? The idea is this, right? When it comes to deflection angle or the EOM ratio of positive rays, right, some different things happen. Some different things happen, right? So if the gas is H2 here, if the gas is H2 here, you would see, if you had seen, let's say, with the gas H2, if you had seen this kind of a deflection angle with the gas H2, if you used some other gas O2, if you had used some other gas O2, but if you had used some other gas O2, the deflection angle differs deflection angle actually differs. That is the most important stuff here. Now deflection angle is like this, right? Let's come up with some linear thing right here. So lamai, the deflection angle varies with the gas inside the tube. If you came up with O2 gas, its deflection angle is less than the situation with the H2 gas. It is a greater deflection angle. O2's deflection angle is less. H2's deflection angle is greater. See, O2's value is less. So when you are coming up with different gases inside the tube, right, the deflection angles, that means the EOM ratios of different gases, right, differ. So that is a very important observation when it comes to canal rays or the positive rays, right? The EOM ratio of positive rays differs with the gas inside the tube. Nothing to do with the anode or the cathode, but it differs with the gas inside the tube, right? Varies with the gas inside the tube. So EOM ratio of H2 is a greater value than the EOM ratio of O2. That is what it says with these deflection angles, right? So that is the idea, right? So take that idea, right? EOM ratio of different gases inside tube giving you different values. So that is the opposite of the cathode ray situation. With the different gases, with different cathodes, you still got the same EOM ratio for the cathode rays, but for the positive rays, right, that differs with the gas inside tube. Let's write the stuff and let's discuss why it happens. Okay, first write the stuff. After that we'll discuss why the EOM ratio or the charge over mass ratio differs with the gas inside tube, right? Okay, just write number 4, the fourth property of positive rays. Just write the nature of positive rays. 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 Come to the red color and write. Come to the red color and write. Depend upon the gas taken in the discharge tube. Depend upon the gas taken in the discharge tube. Depend upon the gas taken in the discharge tube. Depend upon the gas taken in the discharge tube. Right? Put a dash and write. Put a dash and write. Put a dash and write. Different gases are different types of positive rays. Different gases give 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 different types of positive rays which contain particles having different masses. 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 Right? Write these two examples, Lama. Write these two examples. Write these two examples. For H2 gas and O2 gas. For H2 gas and O2 gas. Right? This is how the things are produced. When it comes to H2 gas, when you are applying high voltage, when you are applying high voltage, right? First the H2 bond will break. First the H2 bond will break and produce atomic hydrogens by applying this electrical energy. First this bond will break and produce atomic hydrogen, then two of atomic hydrogen, then those atomic hydrogens will get ionized. So two of atomic hydrogens get ionized to produce two of H pluses and two electrons. As two of atomic hydrogens are ionized, two electrons will be produced. That is how the positive rays are generated from the H2 gas, right? And when it comes to O2 gas, if you apply some high voltage, when you have O2 gas in your tube, right? So the O2 will produce two of oxygen pluses and two electrons, right? Actually, these are the cathode rays. The electrons producing from the H2 gas and the O2 gas. You see, both are same. Even from the H2 gas, even from the O2 gas, you produce same cathode rays. But when it comes to anode rays, or the positive rays, right? You clearly see those differ. These are the positive rays. These are the positive rays. Originate from the gases. So you clearly see with H2 gas you get the H plus as your positive rays. With O2 gas you get O plus as the positive rays. So even though both are carrying the same charge, the H plus and the O plus both carrying the same charge, but the mass differs. The mass of H is a smaller value and the mass of oxygen is a greater value. So even though the charge is same, the mass differs. So the point is this, no? So the charge is same, but mass of, when it comes to mass, the mass of H plus is actually smaller than the mass of O plus. So the EOM ratio, when it comes to EOM ratio, right? The EOM ratio of this thing will be greater than this thing, because the point is, right? When it comes to EOM ratio, right? When the mass drops, EOM ratio increase, no? Right, no? When the mass drops, EOM ratio increase because you are carrying the same charge. When the mass drop, the ratio increases. So EOM ratio of H plus is a greater value than the O plus. So different gases produce different deviation angles, or different gases comes up with different charge to mass ratios for the positive rays, right? So that is the idea. So now I just write this stuff. No need of writing these ones, right? But just write this thing written in blue color. Just write the things written in blue color. These things. Just complete this stuff. If you need, you can complete the black color things as well, but at least just like this. So with H2 gas and O2 gas, you are producing same cathode rays, but different positive rays, right? But the idea is complete. Right, no. Share me that. You had completed stuff, no? Okay. Right. So it is very important, na? So when it comes to positive rays, right? the EOM ratio of positive rays will differ according to the gas inside the tube. When you are changing the gas in the tube, the EOM ratio of positive rays will change. That is the idea. Right now? Okay. Right. Done. Right. So you have written this thing. Just write after this. After this, just write. Put a dash and write. Put a dash and write at the fourth point. At the fourth point. Just continue the fourth point, right? And put a dash and write. Therefore, write it in red color. Write it in red color. Yeah, just continue the red color. EOM ratio is not a constant for. EOM ratio is not a constant for. EOM ratio is not a constant. EOM ratio is not a constant for. EOM ratio is not a constant for positive ray particles. Positive ray particles obtained from different gases. Obtained from different gases. EOM ratio is not a constant for positive ray particles obtained from different gases. Obtained from different gases. Right now? Okay. Those are the 4 properties we need to discuss under positive rays, right? So we have discussed 4 properties of positive rays here, right? Okay. Right. Next point. So yeah, that is all about the properties, right? Then let's discuss about the fundamental positive particle, right? The finding of the fundamental positive particle. Let's discuss about that thing, right? So actually this story is all about finding the fundamental particles, no? So all started with the Dalton. Dalton said that the fundamental, the uncuttable, indivisible particle of matter is atom. It was Dalton's idea, right? Nowadays we know that it is not true, right? But they look for a fundamental particle of matter. The Democritus and the stuff even, right? So then the Stoney came up with the idea of fundamental charge. Stoney came up with the idea of fundamental charge, the electron, and Thomson found that thing, and they found that it is with a negative charge. So the fundamental negative charge carrier or fundamental negative charge is the electron. So the Goldstein came up with the positive rays. Goldstein came up with the positive rays. Then they started to look for the fundamental positive ray, the fundamental positive particle, right? So fundamental positive particle, that is also something with interest, right? The fundamental, the uncuttable, indivisible, tiniest positive particle. What is that? What was that? Right? That was the question here, right? Then with the use of these deviation angles, they have carried out this experiment, right? A few more experiments. Yeah, they have carried out this experiment with using different gases. They have used H2 gas, O2 gas, some other gases, helium, neon, argon, right? Chlorine gas, bromine gas, with the use of various gases here, right? They have found the deviation angles. With various gases, they calculated the deviation angles, right? That means the EOM values, right? They calculating deviation angles means EOM values, EOM ratios, right? Okay. So they have found that after calculating for various gases, they have found that the greatest EOM ratio, the highest EOM ratio was observed with H2 gas. When H2 gas is at the tube, they have found that the highest EOM ratio, the highest division angle, is obtained when the H2 gas is at the tube. So that the positive ray particle of the H2 gas, the positive ray particle which is the H plus of the H2 gas, positive ray particle which is the H plus, you have seen here the positive ray particle of the H2 gas is H plus, right? Okay, the positive particle of H2 gas is H plus. Actually, that is referred to as the lightest positive ray particle then. Why? The greatest EOM ratio means, that means you are dealing with the smallest M value. The greatest EOM ratio appears when the M value is the smallest. The smallest M value gives you the greatest EOM ratio. When you have a smaller value here at the bottom, the total thing is high. So greatest EOM ratio is obtained with smallest M value. So that means as they have seen the greatest EOM ratio with the H2 gas, they have concluded the smallest positive ray particle is actually the positive ray particle coming from the H2 gas, that is H plus. So this is the smallest positive ray particle. So that is ultimately concluded as the fundamental positive particle, the smallest, tiniest positive particle, right? So the H plus, which is known as the proton, is referred to as the fundamental positive ray particle. That is how the fundamental positive particle, right, is discovered, the proton. Actually, this was discovered by the Rutherford, scientist Rutherford was the one who discovered the proton, the smallest, the tiniest positive ray particle, the positive particle, right now? Okay, let's write that story, and let's go to that story, which is indicated at the bottom of the page number 9. Let's go to that. See, it says, in 1907, a study of how these rays were deflected in magnetic field. So this can be used, right? The study of how these rays were deflected in magnetic field revealed that not all the particles making up the rays were with same mass. Revealed that not all the particles making up the space rays were with same mass, and the lightest ones formed when there was some hydrogen gas in the tube. When there was some hydrogen gas in the tube. When you have hydrogen gas, the greatest EOM ratio is obtained. That means the lightest mass is obtained. So that the mass of any other positive ray particle is multiplication of the lightest positive particle. Therefore, it should be a subatomic particle. It should be some subatomic particle. The point is this, Lama. If this guy's mass is equal to x grams, let's say, if this guy's mass is equal to x grams, I just put x grams, right? The other positive ray particles, the other positive ray particles came up with other gases, are carrying some masses which are actually multiplication of this x. Like if you are to deal with the O2 gas, its positive ray particle O plus, right, comes up with some mass which is equal to 16x, like that. So if you are to think of some other positive ray particle, the N2 gas, that will come up with a mass which is equal to kind of 14x. You see, the positive ray particles coming from other gases are actually with some masses which are actually multiplication of the smallest positive ray particle, which are actually multiplication of smallest positive ray particles, these 16 times, these 14 times, like that. So that one can say these are actually formed by some addition of these particles. Addition of some fundamental positive particles will form these. That is the idea, right? So, so that we can confirm this should be the smallest or the tiniest positive particle, right now? Okay, that was what it said, right? The mass of any other positive particle is multiplication of the lightest positive particle. Therefore, it should be a subatomic particle, right now? Got the idea? Okay, these lightest positive particles, that is H plus, were named as protons by Ernest Rutherford. So Rutherford is honored as the founder of the positive particle of the proton. The founder of proton is actually Ernest Rutherford, right now? that is actually the story of the positive rays, right? After that, some properties, some few properties, I mean the charge of the proton and the mass of the proton also found, right, by the scientists, right? Let's go to those numbers as well, right? Let's write the numbers for the charge and the mass for the proton as well, right? So for the proton, right, and next page, you have some properties of protons, right? Just write these things. So the mass of proton, is actually 1.6 into 10 to the power minus 24 grams in grams, right? For the mass of electron, it was 10 to the power 28 grams. It's 24 grams, right? In small ages, you know that protons are heavier, very heavier than electrons, right? So it is basically 1840 times greater, right, with mass compared to the electrons, right? Okay, so the charge of proton, is actually the same charge. The charge of proton is the same as the electron's charge. The same charge in coulombs, that is a fundamental charge in it. To neutralize the charge in electrons, we have used the protons. That is the idea. The fundamental charge carriers, both the proton and the electron are with the same 1.602 into 10 to the power minus 19 coulombs, right? The same charge, right? So we should know another concept called as relative charge. The concept of relative charge. So the concept of relative charge for proton is actually, relative charge of proton is plus 1. Relative charge of proton is plus 1. If you are looking for the relative charge of electron, it is minus 1. Relative charge of electron is minus 1. Relative charge of proton is plus 1. I'll discuss a bit more about the relative charge concept, right? First of all, just write this stuff at the space given at the page number 10. Some properties of protons at that space. Just write these three things, and then after that I'll discuss a bit more about this concept of relative charge, right? Just write this stuff. So mass of proton is 1.6 into the minus 24 grams. Charge of proton is 1.602 into the minus 19, right? And the relative charge of proton is plus 1, right? Okay. Right. Let's discuss a bit more about this concept of charge and the relative charge. Right. Right. Concept of let's write this now. Concept of relative charge. Let's discuss a bit more about that. Concept of relative charge. You have some space there. We'll just write. Right. The point is this. Let's go to some examples. Right. The point is this. Let's consider sodium. Sodium plus. Relative charge means the charge indicates here. The charge indicates here. That is a relative charge. So here the relative charge, is actually plus 1. What we indicate as charge here is actually relative charge. That is not the actual charge. the SI unit of charge is actually coulombs. SI units of charge is actually coulombs. Right? So charge is the unit. So actually this is not the actual charge. This is relative charge. If you need to come up with the actual charge, it should be mentioned in coulombs. Coulombs unit. But if it's small, it's just what we refer this thing as a charge, but that is a relative charge. Remember that. So what is the actual charge then? What is the actual charge then? Actual charge is actually 1 into that smallest charge unit. 1 into the smallest charge unit. Actually, relative charge means, right? Relative charge means, right? 1, right? Here, the relative charge means 1. That means actual charge is 1 into the smallest charge unit. Right? See another example. Let's come up with another example. See this CL minus. CL minus. So the relative charge is minus 1. Relative charge is minus 1. Minus 1. This is what it indicates with the chemical symbol. But the actual charge is actually 1 into the smallest charge unit. 1 into smallest charge unit. Remember, the actual charge is always a positive value. Always a positive value. I mean, you don't, the actual charge won't come up with minus values. Actual charge is always a positive value. Right? Like mass, do you have minus masses? Do you have any kind of minus 2 grams? No meaning there, no? Right? So like that, charge is another property, like mass. Right? The mass is actually kind of a property for matter. Charge is actually kind of a property, right, with charged particles. Mass for matter particles. So Coulombic charge can't be a negative value. Relative charge can be. Relative charge means, right, the charge you are with relative to the smallest charge unit. The charge you are with relative to the smallest charge unit, or the charge you are with relative to the charge of the proton. That is actual relative charge. Charge you are with relative to the charge of the proton. This is relative charge. Actual charge is the charge, the charge actually you are with. Right? That is the idea. Let's come up with another example. Let's come up with the same thing for the sulfate ion as well. SO4 2 minus. Right? SO4 2 minus. So what is the relative charge? Relative charge is minus 2. What we are writing here is the relative charge. Then what is the actual charge? Actual charge is 2 times of the smallest charge. 2 times of the protonic charge, the smallest charge. Always remember, when you are writing actual charges, you don't write the signs here. You don't write the signs here. Right? You don't say, no, when you are writing the, when you are coming up with the mass, you don't say the plus 2.5 grams. You are not saying like that, no. You are just saying 2.5 grams, 5.8 grams, 15.2 kilograms. You don't say like plus 15.2, minus 15.2, no. You are not coming up with any kind of sign there for the Coulombic charge. Right? When it comes to relative charge, yes, you need to come up with the sign. Charge relative to the proton's charge. If the charge is opposite to the proton's charge, If the charge is opposite to the proton charge, it is minus. If the charge is same as the proton charge, same sign, right, it is plus. That is the idea. So let's come up with another one, kind of magnesium 2 plus. Then the relative charge is plus 2. That is what we indicate here. The actual charge means the coulombic charge. Actual charge is 2 times of the smallest charge. Right now, that is the idea, right? So that is the concept of actual charge and the relative charge, right now. So just complete this stuff as some examples to understand the concept of relative charge and the actual charge, right? Okay. So what about the electron? What about the electron? Actually, electron can be written like this, E minus. So for the electron, the relative charge is minus 1 and the actual charge is 1 into this 0.2 1.0602 into the power minus 19 coulombs. When you are writing the coulombic charge, you don't put any units, but the relative charge is minus 1 because the charge of the electron is opposite to that of the proton, right now. Okay, that is the idea, right now. Right. So with this thing, we'll wind up the session for the day, right? So with the next lesson, we can discuss about the atomic models, right? With the next lesson, we'll discuss about the atomic models. Today we have just completed the finding of the fundamental positive charge, which is the proton, right? Today's story was about the proton, right? So basically the experimental setup, first experimental setup came from the Eugen-Goldstein, right? And the proton is actually confirmed by the Ernest Rutherford as the hydrogen's positive rays came up with the greatest EOM ratio and the smallest mass then, right? So the proton is confirmed by the Ernest Rutherford through that experiment, right? Okay, and the proton's properties were discussed, and that is all about the today's lesson, right? So that is all about that is all what we need to know about the positive rays, right? Let's wind up for today. Then we'll see with the atomic models, the Thomson's model and the nuclear model and the stuff next day around, right? Thank you and good night then.